This. Okay, good. Well, thank you very much for the opportunity to present here my work. So for those who don't know me, I'm immunologist. I'm a postdoc at the University of Reading, currently part of the XAIDA project. I'm working with Ted Shepard and Dr. Marianne Kretschmer. I'm focusing on analyzing the effects of cold extremes and wind droughts on the energy sector, specifically over Europe and mostly during the winter. So we'll give first a quick introduction and motivation. So essentially, you're probably aware that due to climate change, our energy network has to move to using more renewable energy sources. And some of these energy sources, especially specifically wind and solar, are highly dependent on weather. And this can be highlighted by looking at weather regimes. Here is an example from an article from Van der Wiel and colleagues from 2019, where you will see that Scandinavian blocking regime, you have quite low renewable energy production, and at the same time, you have quite high energy demand due to cold conditions. And this leads to high energy shortfall. Now, shortfall is essentially the discrepancy or the difference between energy demand and renewable energy production. Now, since we are moving to more and more renewable energies, understanding these particular periods is really important. So the focus of this presentation is really to look at these high shortfall periods over Europe during the winter and look at the influence from weather regimes. Also, I will be highlighting some differences between European countries. So to give you some background, I'm going to discuss a little bit the data that I'm using. Firstly, the energy data has been taken from Bloomfield et al. From 2020, and essentially is modeled energy data derived from ER5. So data that I'm using is energy demand, solar and wind capacity factors. So capacity factor is essentially the ratio between the actual power output and the theoretical maximum based on the installed wind capacity, for example. Now, this dataset covers the periods from 1939 to 2019 for 28 European countries. I'm using a extended winter period, so from October to April. And an important point for this dataset is that the energy infrastructure, but also the socioeconomic conditions, such as the demography, are kept constant, and the year of reference used is 2017. Additionally, each day is considered as a Monday. As you will be probably aware that, for example, demand varies a lot between a weekday and a weekend day. So all of this allows me to essentially remove all the influence from changes in the infrastructure or change in the demography, and only see variation from energy due to meteorological variables. So to understand this influence, I'm going to be using ER5 data, specifically to meter temperature, the geopotential height at 500 hectopascal, horizontal wind at 10 meters, and incoming solar radiation. So to start with, I will be discussing a little bit some characteristics of these energy variables, and also more specifically what I define as energy days. Now, from the introduction, you gathered that shortfall is basically energy demand minus renewable generation. In this case, I'm focusing on only wind and solar. For the energy days, essentially, the energy extremes. So when considering demand and shortfall, is essentially when the daily demand or shortfall are above the 90th percentile. While for wind and solar, it just means that the corresponding capacity factors are below the 10th percentile. So looking at some characteristics of these energy days, here we can look at the seasonal variation, so the distribution across the different months. And you will see that this distribution really follows climatological variation from the driving variable. So for instance, here an example for France, when looking at the month, you see the months where you have the highest frequency of demand days is mostly the middle of winter, such as December to February, while for wind days, so periods where you have quite low winds, is mostly during the shoulder season, so around October and April, while during the middle of winter, you assume that the conditions are generally stormier. So as the focus here of this study is really to look at shortfall days, it's important to determine what is the influence of other energy events, such as wind and demand. And at the bottom, I'm showing essentially the percentage of shortfall events which coincide with demand, wind, or solar days. And here are some examples for France, Finland, Germany, and Spain. And as you can see here, we have France and Finland where most shortfall days coincide with demand days, while for Germany and Spain, they are coinciding mostly with wind days. And this essentially shows two categories of countries if you want to do a generalization, where you have countries with low installed wind capacity or countries with colder climates, where shortfall is mainly dependent on demand, so mainly dependent on colder conditions, while for countries with higher installed wind capacity or countries in milder climates, these shortfall days are going to be more dependent on wind. Now looking at the duration of events. So here I define event as basically just consecutive days. And I'm going to differentiate between longer energy events, which last for at least 5 days, and also look at brief energy events, which are 3 days or shorter. And as you can see here, looking at the normalized shortfall, you will see that during longer events, both the maximum value that you can have, but also the average value during an entire event is higher during longer events than during brief events. This can be due to, for example, the buildup of cold air. However, there is no correlation between this and the persistence of weather regimes. As you can see here, the persistence of the weather regimes is fairly similar between long and brief events. However, you will see that the regimes are generally already quite persistent compared to their climatological persistence. Meaning that for the recurrence of an energy event, whether short or long, you will already need a persistent weather regime. Lastly, to discuss some characteristics of energy days, we can look at the trends. So in the middle, I'm showing the yearly frequency of demand days for France, and also the average DGF temperature, so December, January, February temperature for France. Both of them are highly correlated. And as you can see here, we have a decreasing trend in demand days, while at the same time you have an increase in temperature. So probably due to the increase in winter temperature. However, what you can see is similar to before, is that for shortfall events, there is a difference between the countries with low installed wind capacity and countries with higher installed wind capacity, where, for example, the shortfall trend is similar to demand for countries with low installed capacity, while for countries such as Germany with high installed wind capacity, the decreasing trend in shortfall days is less strong. So as I explained before, the I will be discussing the influence of weather regimes. So here I'm going to describe how I compute these weather regimes and describe them more in detail. So the construction is fairly similar or fairly classical to what you would see elsewhere. So I'm using the daily Z400 anomaly data and applying a k-means clustering algorithm over the entire dataset from October to April. And I selected 6 regimes. On top of that, I will also do a regime attribution. So this means that each day is attributed to one of the regimes by constructing indices, so one index per regime. So indices are a normalized projection of the daily atmospheric circulation onto the regime composites. And essentially what I'm doing is for each day, I select the highest index. If it's above the standard deviation, then this day is attributed to the corresponding regime. This essentially allows me to filter out all the days where the atmospheric circulation is too dissimilar to any of the regimes that I selected. So they are considered as mutables. So on this next slide, I'm showing what these regimes look like. You will recognize classical weather regimes such as NAO negative, NAO positive, Scandinavian blocking, and Atlantic ridge, but also some counterparts such as the Scandinavian trough and Atlantic trough. So since we are interested in the influence of the weather regimes, here I'm looking at the surface impact of these regimes. So looking, for example, at NAO negative, Scandinavian blocking, and Atlantic ridge, you can see that they are associated with colder conditions, which potentially could lead to high energy demand during the winter. Similarly, these weather regimes also can lead to quite low wind conditions. As you can look here at lower wind conditions or negative wind anomalies over certain parts of Europe. As we had a look at frequency trends for energy days, let's have a quick look for the weather regimes themselves. And specifically looking at Scandinavian blocking regimes and Scandinavian trough, you will see an increase in frequency for Scandinavian blockings, while there is a slight decrease for Scandinavian trough. Important to highlight at this point that there's quite a high variability between years. But as we saw before, Scandinavian blocking regimes can lead to quite cold conditions and low wind situations. So they might affect the frequency of demand days. However, as we saw before, looking at the frequency trends of energy days, these might be already counteracted by a warming climate. Now coming to the most interesting part of this presentation, I hope, which is really looking at the influence of the weather regimes on energy days. So first, just have a quick look at here's the energy distribution for different weather regimes. Here an example for France, looking at energy demand, wind and solar capacity factors, and also energy shortfall. And you will see that each curve is representing one of the weather regimes. Now, at first glance, it's quite difficult to disentangle between all of the regimes, so to identify which regime is going to lead to one particular scenario. However, if you look more specifically, so looking at the conditional probability of, for example, demand days occurring during different kind of weather regimes, we can really highlight that some regimes, such as Scandinavian blocking, Atlantic ridge, and NAO negative, are much more favoring the occurrence of, for example, demand days or shortfall days. Now, to get a bigger overview across all European countries, we can have a look at this map, which shows that for using each color here, represent essentially the weather regime with the highest conditional probability of having a shortfall day. With the stripes here showing essentially weather regimes where this the second weather regime with the highest conditional probability, which is within 1% of the weather regime with the highest conditional probability. So essentially the first two have a very similar conditional probability. And as you can see here, we have three main weather regimes that affect Europe. And specifically for Scandinavian blocking regime, you can see that it could affect potentially large part of Europe. That means that we can assume that if you have a Scandinavian blocking day, there's a probability that a large part of Europe has a lot of stress onto his energy network. Now, to further investigate this, I had a look at how well Europe's energy network is interconnected. Now, there's many ways how European networks are interconnected, both within and outside of Europe. But one way is to look at regional security coordinators, which are essentially entities which regroup national transmission system operators together and help plan and prepare for energy, very extreme energy situations. So I think it's fair then to assume that all countries within each of these regional security coordinators are going to be well connected together and well coordinated. So the question then is to ask whether if all countries within an RRC experience a shortfall day, what would happen? So here is an example looking at the Nordic RRC, where you will see here the purple lines showing the countries part of this RRC. And here I'm looking at composites doing all shortfall days that occur at the same time in all 4 countries. And as expected, you can see that within all these countries, we have quite high normalized demand, also quite high shortfall, but also quite low wind capacity factors. But an important thing to observe is that neighboring countries, especially closest neighbors, will have also quite high normalized demand, but also quite high normalized shortfall at the same time. Meaning that if they wanted to mitigate the impact of such extreme situation, connecting to neighboring countries might not be the best or might not be sufficient. This can be further highlighted looking at this map, where I'm essentially showing the percentage of these common shortfall days, so shortfall days that occur in all 4 countries, and looking at the percentage of these days that also that occur at the same time as shortfall days in neighboring countries. So essentially showing that for the most neighboring countries, they will also experience shortfall days at the same time as all 4 of them, while further away countries are less likely to experience high shortfall. As expected, when looking at the regimes which are responsible for this kind of situation, we can see that they are the same culprits that we saw before. So blocking type regimes such as NO-negative, Scandinavian blocking, and Atlantic Ridge, as shown here with some example of 3 RSCs. Further on, if we look at the composite for Z500, so looking at Z500 anomalies, here we see essentially a ridge formed over Western Europe, and what will dictate which country is going to be most affected is the position of this ridge. Now, if you want to push this even further and look at a potential worst case scenario, I had a look at the coldest winter of the 20th century. So specifically the winter 1962 or 63, which interestingly was characterized by a very persistent NO-negative from mid-December. You can see here some composites for DJF. So again, we recognize this anomaly, this ridge formation over Western Europe, quite cold conditions. Just to highlight that here I had to extend the scale to account for the particularly cold condition during this winter. And also, you can see quite low wind conditions across northern Europe and more specifically over the North Sea. So you might probably argue that there's quite a low likelihood that this type of winters is going to happen, especially within a warming climate. However, there's a paper from Sipel and colleagues, which quite recently showed that while the likelihood is quite low, it's not even possible. So here, an interesting thing to look at is what would be the impact of such a winter on our current energy network. So here I'm essentially looking at composites across the entire winter, so for the December, January, and February period. As you might recall, the data set that I was using covered the period from 1939 onwards. So I'm using another data set from the same author. And unfortunately, both for wind and solar, only 12 countries are represented out of the 28 that we had before. So it does mean that for shortfall, all these grayed out countries don't have data. So it will be a more limited view of this particular event. However, for demand, we can see for all countries that we have quite high normalized demand across the entire winter. And for shortfall, it's a slightly more mixed picture. It is also important to know that these are composites for the entire winter and that the really cold conditions only started around mid-December. So now looking at the frequency of the energy days, in these figures, I'm looking at the frequency ratio. So the ratio between the actual monthly frequency, so for example, for December, compared to the climatological frequency. And as I showed earlier, for example, in December, January, and February, these are the months where you have the highest frequency in energy demand days. So here we can see that for most countries, they would experience 3 to 6 times the amount of energy days that they would generally experience. And for shortfall, it's a bit less, but for most countries, it would still be around twice the regular amount of shortfall days. So here to conclude, we saw that essentially we have extreme energy shortfall, which is highly dependent on demand and wind generation, here specifically for winter. The proportion varies with regional climate, but also installed wind capacity. Also, we saw that a subset of regimes can affect large parts of Europe, potentially leading to simultaneous high shortfall across multiple countries. And when looking at this worst case scenario, this highlights what the current and also future energy network of Europe needs to be prepared for, especially with higher proportion of renewable generation. So showing that interconnections is key, but might not be sufficient for a resilient energy network, especially if we are limited only to our closest neighbors. So I will finish here, and if you have any questions, I'm happy to answer them.
Hi, Emmanuel. Thank you for the presentation. A nice overview. I had a few questions, and I'm sorry that I missed the first 4 minutes, but I couldn't enter the Zoom normally due to restrictions of my employer. You mentioned you were clustering the European regions for the network using the different societies. Is that the best way to go, or do you think it might be more suited to look at the transmission capacity, because that should also be available, or that actually is available? And what is the reason that you chose the collaborations that are mostly on the network security side, on the actual not the infrastructure, but the regional action committees for in case of disasters. So what is the choice that you made there? Because I don't follow that.
Okay, so the choice mostly is partly about simplicity. So in the sense that here it's model data, which doesn't include any transmissions between different countries. And also these regional security coordinators, since they are really focused on extreme energy situations, which I'm also looking into, I thought it would be quite appropriate. Also, I believe that they are getting more operational power now within Europe. So there's a change where before they were just advising. Now they, from what I understand, they should get more operational power. But yeah, it's quite a simplistic view to get an idea. It was just wondering when I looked at all these weather regimes, okay, what happens if multiple countries are affected at once?
Yeah, okay. Then I do think it's important to look into that because
yeah,
those councils, those security councils, they work on other threats than actually weather generally. The current report and the current rebuilding of that report is taking a bit of weather into account, but by far not what we are talking about here.
Okay.
They are more looking into effects like, is there coal available? Is there gas available? And that is then transported, for instance, between those regions or coordinated between those regions. Comparing and clustering France and Spain, given the transmission capacity between those regions, I think is not relevant. There's like 2-3 gigawatts, maybe 6 gigawatts of transport capacity between those countries. While Spain alone has a peak of demand of like 40 gigawatts, so never adequate.
But I think it's still relevant in a sense to highlight the fact that if you were to connect only between these two countries, if you assume, for example, that you have better interconnection, then if both are in a dire situation, maybe it's not the best situation. So it's also a suggestion as Europe is moving into increasing their infrastructure for interconnection, but also in storage side, that these type of solutions would be more appropriate, for example.
Okay. Very cool. Thank you. I'll leave the floor for others first.
Yeah.
Yeah, thanks, Emmanuel. Very interesting talk. So I first have a question and then maybe more a comment. So the question is to your 1962-63 case. So I thought that was really interesting. So so the way I understand this is that you're basically you're using the event as it happened, the meteorological event.
Yes.
As it happened in that winter and project that on basically the current energy system. Is that right?
Yes, that's correct. Yes.
And then you mostly look into power and the power network and less so into other energy drivers. Like what Laurens was also raising, maybe like gas supply or coal.
Yeah. So since this data set, I really only have the mount, wind and solar. So it has its limitations since I'm only considering renewable generation. I'm also not considering, for example, the hydropower and such, or nuclear power. So it has some of these limitations, but it also, since it's using UR5 data, it means that it has this homogeneous components that allows for having essentially the same model across 40 years. So looking at variations that are only weather driven. So it's really removing any factor outside, such as political or economical situations.
Right. But I would think like for energy shortfalls in winter, isn't that like heating the key problem, and which might be in many countries mostly gas or not?
Yeah,
Not that simple. I mean,
yeah, it's not that simple. For example, for France, most of the heating will be electric.
okay.
But of course, France has high nuclear installations. But yeah, so it's mainly driven through heating for during the winter at least.
Yeah, the other question, which is maybe more of a comment, but I was quite intrigued that Scandinavian blocking is this kind of high impact type weather regime.
Mm-hmm.
And I wonder how seasonal predictability can help here. Where, I mean, my understanding is that some weather regimes might have better predictability, longer lead predictability,
Mm-hmm. Yeah.
and how that can support. Have you thought about that?
I haven't looked at the predictable side of this. I think Scandinavian blocking is one of the regimes which generally is better predicted, partly due to its persistence compared to other regimes. I haven't really looked at which drivers might influence the predictability. I think a lot of studies have been done more on the NAO plus, NAO minus, and influence, for example, of MJO, but less so on Scandinavian blocking. But yeah.
Okay, thanks.
Yeah. Yeah.
Yes. If anybody else wants to answer questions, please go. But you were showing and looking into some trends, and I know I probably missed this, but you use ERA 5. The back extension by now already goes back to 9040. Would it be possible to also apply that a bit longer? Because 40 years for trend analysis is maybe a bit vague given the variability that's observed.
Yeah, definitely for regimes, it would be more appropriate to look at longer period. Of course, I'm limited for the energy data to this data set starts from 1979. The same author has a data set starting in 1950, but as I said, it doesn't have wind and solar capacity factors for all the countries for the entire period. So I thought a good compromise would be okay, limit to 40 years, but have a larger data set in covering more countries. Yeah.
That then maybe the logical follow-up step is, would it be possible to make it yourself, or what would be needed for that?
Yeah, it would be interesting to make it myself, but I think one of the next steps within the XAIDA project is more to look at projection on a climatological side. So here is really just an analysis of current situation. But then what one of my objectives is looking at two types of projections, in the sense of looking at the projection from the political side of how much installed wind capacity is going to be, how much is going to be installed in 2030, 2035, and so on. Same for solar, and see how does it impact, for example, distribution of this particular energy extremes, but also then looking at projection on a climatological side and see how this evolves. So that's more the direction that I will be taking.
But you would still need to make those models for the projections, right? You still need to make the impact model for the projections,
Yes.
so you would also need to.
Yeah. So for this, I believe the same author has some data based on, I think, Eurocodex projections. But I will have to look into this, because I believe that the author basically just did a basically just shifted the temperature, for example, by the expected average temperature at a later stage. So I will be looking into this and maybe use actual projection and constructing the data myself. For demand, I've already done that from 1950 onwards, so this would be easy to do. For solar and wind, I will have to see how I will do that. I haven't thought of it right away, how to do it on a technical side.
I will just have more questions. Sorry. No, but maybe I don't know what the time scale is you're working on, but at NSOE there is currently the development of the Pan-European Climate Database that's going to be open. If you want, I can see. I can definitely notify you when that is available via the CDS because it will no longer be a closed data set. But if you want, we can discuss if there's also an option to share a subset already under an NDA before the official release, because that might take another month or two. But it depends a bit on the timeline you're involved in.
Yeah, I think I will probably be looking at projection more on end of this summer. I will start with this, so I will still have a year. So I think probably can wait for official release of the data set, and yeah.
Okay. Then a final question, but just maybe more of a comment.
Sure.
Hey, you mentioned a few data sets and you mentioned a few things. I would very love to see the references of the work you've done and the data sets you've done, and to have a bit more information on that. Maybe good to include that also in the future in your slides. Allows for a bit more transparency of what you do. This is really more a general comment.
Yeah,
if you have a
is mentioned is coming from Bloomfield 2020. I don't know if we are going to be sharing the slides in any way. I have the reference within the slides here. So it's oops. So
no, I know exactly which data set you used.
yeah. So
Anna's data set on the R5 projections.
Yeah. Thank you for your interest. I believe Jean-Pierre wanted to say something. You were muted just before.
No, thank you very much. It was very interesting.
Thank you. I don't know if there were questions in the chat. I haven't seen them. Right. Thank you very much. Thank you.
Thanks, Emmanuel. Very interesting.